I'm going to work on encoding the SIB bytes now for scaled index effective addressing. So I'm going to focus on these rows in the ModRM table. So as soon as mod equals something with rm being this 100 here, it means that we need a SIB byte. And the main reason outside of the sort of RSP or EBP exceptions here, or the RSP or RBP exceptions here, is basically to use a scaled index. So I think we'll just start again with generating some test cases. So we'll remove all of these. There are quite a lot of test cases to go through, so I'm just going to stick with 32-bit operands. So we'll start with, for example, a normal register. Let's say, I don't know, RDI multiplied by 1. This multiplied by 1 is actually, there's no point in using a SIB for this, but the point of this test is that if I generate an operand that is, no base with a scaled index multiplied by 1, I should simplify it to just the direct access that you'd expect. So we'll move, let's say, ECX into this one. We'll use the problematic registers. We can't use RSP as an index, so we'll skip that one and we'll use RBP. The other two are going to be R12 and R13. So we'll just move some random registers into these. And I think that should do. So we've got some exceptions here. And then maybe we'll have one more, which is just some other extended register. So we'll say R14. And that can have another extended register moved into it. Let's say R9. So we'll also want to cover a scale of 2, a scale of 4, and a scale of 8. So this is all of the no base, no displacement ones. These ones will be no base with a displacement. And there's also 32-bit displacement. So then if I copy all of these ones, then we can also do the same tests but with a base register. And for the base, I'm just going to copy all of these and just have the same one, except for the final ones, which were going to be R14 here. So these R14 ones, we can use SP as a base. So I'll use RSP as the base in these ones. I think that should cover enough cases for now. So let's just assemble this. We've got test cases.asm, output test cases, ndisasm, b64, test cases, okay. So we'll just take all of these. Take the expectation. Here's the instruction, followed by the expectation. Okay, so now I just need to go through these. We can see here that NASM has actually simplified these multiply by 1 cases to just a direct access. I'm going to change these back to multiply by 1. so that it represents what the test is actually going to do. And it's also put in these zero displacements for special cases. So we'll get rid of those. And then it's simplified the multiply by 2 here. So in the case with no base, it's simplifying multiply by 2 into base plus a scaled index of 1. Because that would be the same, and I believe it's the shorter encoding. Because if we look at the SIB notes down here, if we have no base down here, if we have no base, we could do, for example, say EAX multiplied by 2 with no base, which is this this asterisk column here. But then in that case, we require a 32-bit displacement. So that's an extra 4 bytes on the end that we'd have to include. Whereas if we converted this into just having, a base with a single scaled thing, so, if it was this just EAX with, EAX here, then we only need the SIB. And I don't think we would need any displacement in that case, so we would save at least 4 bytes. At the very least, if we did need a displacement, we'd save 3 bytes. So it's a shorter encoding for the same thing. But I'm going to change these again to just multiply by 2, just to show what the test case is actually going to do. So I'll have to do the same here. So this is multiply by 2. I think I missed some multiply by 1s. So this is multiply by 1, 2, 4, 8. This is multiply by 1 here. These ones should be multiplied by 2. This is testing the base index. So these ones are this is not a multiply by 2 test case. This is a multiply by 1 test case. And then the rest of them look like they should mostly be the same. So these ones are multiplied by 1 again. And then these ones are also multiplied by 1. Okay, so let's just fill out the operands for the first 5 lines here. So do dword. The way that I'm going to do this is basically the base will be the first thing. So we'll create a new register called NB. That can represent no base. We're going to do a memory access, and we're going to use a scaled index of DIX1. And then the operand that's going to go into that is going to be CX here. So let's just copy this into the other ones. Okay. So now we just need to change these. So this will be a BP, this will be R12, this one is R13, and we've got R14. So this one's going to be R9. This one is DX, this one is AX, and this one is R15. So let's just copy all of these to the other ones. So this is the same, but the test is multiplied by 2 instead. This one is multiplied by 4. And then these ones are multiplied by 8. So now I can just take all of these and move them down to these ones. So these are the same tests, but they have a displacement of OX7F. And then again the same thing down here, but these are the tests for the displacement of the 32-bit, so this is OX7F, FF, FF, FF. And now we can take all of these tests and copy them down into the base ones. And the only difference with the tests here is that we have RSP as a base. So if I just go and find the first one, so in these cases we've got NB, this is going to be SP as the base. And then the rest of these no base ones are going to be changed so that they use the same register from the index as the base. Okay, so this should compile, but or this should run, but we'll get some errors about undefined operands and things. So we're going to find those now. So we need a new register called NB, and this is a special placeholder one for no base, so I'll mark it as no base. And no base is the same as BP because it's this asterisk column up here, which is the value 5. Then we need scale. So scale, I'm going to say, is this other type. And scale is that 2-bit field, so we can actually use iota the same way that we do with size here. So this would be x1, x2, x4, and x8. So this will be the 0, 0, then we'll have 0, 1, then we'll have 1, 0, and then we'll have 1, 1, because this will be 3. So that will give us the scale field for the SIB. Then we need a helper called SI on here. So this will take the index operand along with the scale. And it's going to return a new operand, which we're going to mark as being scaled index. And we have this other flag called expecting SIB. So if something is a scaled index, it always expects a SIB. So we'll just use that straight away. And then what I'm planning to do here is that right now this this o.value field, this is a 64-bit integer, and right now we're only using the low nibble. So this is nibble 0 here. We're only using this low nibble for the ModRM. This is either going to be the RM or the reg field. So this is the register number, which is used in either the RM field or the reg field for the ModRM byte. So that's just 4 bits there, and we got loads of space to spare in here. So what I'm going to do is that the next nibble up, I'm going to store the base in. So this will be the base. And this is also just a register number, so it will fit within 4 bits. So that's why we can fit it in a nibble. Then the next one up will be the index. Again, this is just a register number, so it fits within 4 bits just fine. And then the next one up, this will be the scale. And the scale is only 2 bits, but we'll just say that it occupies the entire nibble just to keep things simple. So when we do something like saying, .si, when we call si, this will take an index and it will take a scale. And what we need to do is change this rm nibble into OX20, I think. No, not 20. we're going to change it into something. It may be 4. Yeah, I think we're going to have to change this into 4, like hard coded to 4, because 4 is the RM value that's required to say that we're going to use a SIB byte. So before we change this to 4, the operand that we're calling this on is going to be the base. So we need to shift this nibble up into the base nibble, set the RM nibble to 4, then we'll shift the index register number up into this nibble here, and then we'll shift the scale up into this nibble here. And that should give us all of the information we need to start generating SIB bytes for these special like scaled index cases. And then within there, I've seen that we've seen that NASM has done some simplifications. So for example, even if we do this and we generate a SIB byte normally in the most straightforward, naive way according to the tables, we're still going to get some failing cases. So in the case where we see that it's a scale multiplied by 1, we need to do some special logic to transform it into just, a memory access, just a direct memory access. And in the case where we see it's multiplied by 2, we need to change it so that it's going to be a base plus the scaled index multiplied by 1. So this scaled index here will be multiplied by 1. So we're just going to transform a scaled index multiplied by 2 into this one, and we're going to transform a scaled index multiplied by 1 into this one to match up with what NASM is generating as the more space-efficient encoding. So we'll start by just shifting all these nibbles around, basically. Value, we're going to shift up the RM into the base first. So this will be value mask off the RM, which is these lower 4 bits, and then we'll shift it up by 4 bits to get it into the base nibble. Then what we'll do is we'll shift up into the nibble above that. This will be the index. So we'll say, index.value, mask off those lower 4 bits, and then shift it up into that index nibble. And then we're also going to take scale, which we'll need to convert to an int64 first. And then we're just going to shift that directly up into the scale nibble, which will be at 12. Then, because we've already preserved the RM nibble already, now we can set that lower nibble to 4, because in the ModRM table, anytime we see this SIB notation here, we always want, some mod followed by some 2 or some 3 RM. These 3 RM bits are always 100. So if we've got the mod combined with the RM and we just look at the highest 4 bits of those, it always comes out to something, something, 10. Oh, sorry, no, I've got this the wrong way around. So basically it's if we look at the RM, so if we're just treating this as RM, we should be looking at this with the 0 prepended, so actually it's coming out as a 0, 1, 0, 0 all the time, which is why we set it to 4. And then the mod can alter that as we go. So yeah, I think 4 is correct here, not 2. I think it is 4. We'll test this. If it's not 4, if it is 2, then I can just change it. So, but anything could be in those lower 4 bits there, so we need to clear it out first. So we'll do and not equals oxf to clear out the low nibble. Then we'll set it, And I did say in the explanation just a minute ago that we're going to have to special case a scale of 1 and 2. So we've got expecting sib, we also need the scaled index flag. We'll have scale 1 and we'll have scale 2 so that we can check them specifically. Okay. And when we get into here, we'll do a switch on the scale where we'll say, in the case of x1, we'll OR the info with scale 1. And in this case, we'll do 2, so that we can do the special casing when we get to the end of the tests. So still no base. Okay, we need a no base flag as well. Scaled index, we'll say no base over here. Okay, so now we've got loads of failing tests. So we'll try just the straightforward sib stuff first. So if it's memory access, which it will be, because that's the only way we're going to use a scaled index, then we're assuming indirect access, and if we've got a displacement and we're not rip relative, then we'll change the mod to one of the other ones. I think maybe what I'll do here is just add a new case for now, where we'll say that RM is scaled index. So if we're in a scaled index, we need to set the sib to something. And actually, these are going to be incorrect now because, yes, I need to actually change these to get out the correct bits. So let's just change this first, and then I'll go and change these methods as well. So in this case, this is what I'm thinking of with the OX2 for the sib. Because right now we've got the, let's see, right now we do 4 shifted up by 3 for the index. So if we've got this, and then we shift it up by 3, then this is now 4. 1, 2, 3. Yeah, okay, so this is actually... Okay, so this is 4 here. If we shift this up, so we go 1, 2, 3. Then we've got 4 here, and we've got 2 here. So I need to change these methods to unpack the bits that I put into them, which means that RM is, or sorry, base is also going to give us the incorrect. Our base would probably be okay, but I think maybe I'll just use RM here to be a bit more explicit about it. So if we say RM, and then we just hard code the OX20 in here, that should take care of any special case with RSP. And then it means I can actually use RMSS, ordered with rm.index, ordered with rm.base here, and change these to unpack the values properly. So in this case, the base is going to be in the second nibble, so that will be the low 3 bits of the second nibble, and we'll want to shift it down into the bottom nibble for the sib byte. This one is going to be the lower 3 of the third nibble, and then we'll shift this one down so that it's in the middle 3 bytes. So that would be, it's in position 8, and if we shift it down by 5, that will put it in the correct position for the index field. And this one, we need the lower 2 bits of the 4th nibble. So we're in the 4th nibble, lower 2 bits, and we'll shift this down so that it starts at the 6th bit, which will be, it's in position 12 now, so we just shift it down by 6. Okay, so we'll ignore these special cases for now. It looks like we are generating correct code here. So we've got, 4489 and then 3CAD. So this is 4489 3CAD, and then we're just missing a displacement. So with these no base cases, if we go and look at the notes in the SIB table, basically when there's no base, let's see, when there's no base, which is this asterisk nomenclature here, it means that there's a 32-bit displacement if mod is set to 00. So for me, this is address indirect. Otherwise, it means there's a disp8 or a disp32 with EBP as the base. So for no base, we need to make sure that mod is always address indirect, and we always have to have a 32-bit displacement. So it seems like if we're in scaled index, we need to make an exception for if RM is no base. Then RM, there's a few exceptions here actually, so I think I'm going to put these into a switch maybe. So we'll say if RM does not have a displacement, then we'll reset RM to have a displacement of 0. We assume that it's indirect anyway, and we only set this stuff if we have a displacement and we're not rip relative. So in the case that we're no base, if it does have a displacement, we'll want to set it back to address indirect. So maybe in the default case here, we'll set mod equals address indirect. Too many arguments in disp. Oh, this should be D. Okay, and then we actually need to use the displacement. So the problem here is that we're on address indirect and there's no case for actually adding the displacement. So we'll do a switch again. We'll say switch case. In the case that it's rip relative, it can carry on doing what it was already doing. But in the case where RM is scaled index, then we'll do a 32-bit displacement. Okay, so we're getting 32-bit displacements, but these are for like the special cases where I need to transform things. And in these cases, it wants rex prefix. Okay, right, yes. So currently I'm only doing rex prefixes for B, R, and W. And I'm just going to put this one down here actually. So W, R, and B, we should have X in here. So this is, X will extend an index register. So we want to see if RM index is extended. Is index extended, then we want RX. So we need another helper here for is extended. And the scale, if we have one, would be in the third nibble, so that would be 800 in hex, because that would be the high byte of the third nibble. If that's set, then it's extended. And extended actually also needs to include the base, because the RM could be in the base position as well. So we want to check the high bit of the first nibble, but also the high bit of the second nibble as well. And if either of those are set, then that means that the RM or base is extended, because rex B should be extending either the sib base or the modrm.rm. Okay, so that takes care of quite a lot of the tests, actually. So I mean, it looks like this could just be a case of the transformations now. Maybe. I think if we'll do the transformations and just see how many are left. So let's see. In the case that it's going to be, in the case that RM is scale 1, we don't care about displacement or anything here because we're going to transform it into a completely different thing. So we want to do this based on the index because there's no base, the only register is the index. And in the case of a scale of 1 where we've got no base, we just want to transform it, we just want to transform RM into the index register as a memory access. So we need a way to look up the index register. So we just say index. The index is the value shifted down by 8 because that's the position we've put index in, and then we'll mask off that nibble. Then we'll want to use the index to look it up. So maybe what I'll do is I'll say RR for the new register can be some lookup table registers where we look it up by the index. Yeah. So I think I will just take all of these and we'll just make a registers table down here. So we'll just say var registers equals this, which will be a bunch of operands. And we'll index it by the register number, which is what the index nibble is. And we'll set it to the existing register operands. These will be copies of those operands. So if we do that, that's going to give us back a plain register, which we then need to I don't think we have to say M on here because we're already, the only time that we check for memory is here, so we could just skip the M part, but we do need to preserve any displacement that it might have. So we could say that if RM is displaced, then RR equals R.D with RM.disp. So this will preserve the displacement, and then we'll just overwrite RM with the new register. Undefined O. In generator 70, oh yeah, so O should actually be RM. So now we've got these special, okay. I am doing the rex before all of this stuff, but I'm changing RM, and rex is based on RM, so I need to move the rex logic to after all of this. Then we've got some problems here. So we want, okay, so this is the mem-BP case, and this one is the mem-SP case. So we need to do these things separately, I think. That breaks a lot more. It's like if we've got SP, I think I'll do the simply transformation of the x2 case first. So in the x2 case, So if we've got scale 2, we want to do exactly the same thing, but the difference would be that we're transforming it into base plus an x1 scale. So we'll say that if this is a scale 2, then this should equal SI with itself x1. Okay. So this just gives us all of these failures are because of special case BP. So we've got 44, which is the rex. We've got 89, which is the opcode. Then the ModRM seems like it's wrong. We've got X here. So W. Okay, rex is fine. So the case for BP with 1, these are all related to scale of 1 except for the, okay, so the top one got scale of 1. Okay, so yeah, it's just because of special registers basically. So how can I deal with this? So if we've got scaled index, this is the ModRM. So for this one we want 7D. So this one here, we want 7D, which is over here. So that's EBP plus DISP 8. So that's where, if we were doing this BP one, okay, let's split this out into a separate if. Okay, so that deals with the BP one because we want to run this whether we're scaled or not. Then we have this case here where we're doing rex is fine, opcode is fine, the ModRM is actually fine as well. It's just that in this case, for RSP, we need the SIB. And that's where it would be doing this. Okay, so how can I solve this one? So we're saying scale, if the scale is 1, this is looking up the SP register. It's doing any displacement, which would be fine. Oh, actually, in this case, it's looking up R12, but this should still be mem SP here. So, I think I'm going to need to do this somehow. We're going to have to save something like... We set the SIB for scaled index. But the point is that this is no longer scaled index. So if rm.is scaled index, then we'll do this. Or maybe this needs to be an if down here, because this can be overwritten. So if it's this and not scaled index. Undefined RM is. Okay. Okay, that works. That's all of the encodings done. So I think now I'll go back to the test cases. So we'll go to generate a test. we'll take all of these test cases and I'm just going to switch around the operands. So let's go over to here. We'll take the source operand and we'll switch it around so that it goes on the dest operand location instead. Then we'll do the same with all of these. So we'll just select all these, switch them around. We'll do NASM test cases and NDISASM test cases. So let's take all of these and we'll just replace all of the expectations and see if it works. And that's fine. So I think that covers all of the SIB cases. There may be one or two I could be missing. I didn't really check. But if it comes up, I'll deal with it when it happens. If we go to something like MOV in here now, so we've got RM and R, and we've got the other way around as well. There are some special cases of the opcode here that just, assume the A register, so we'll probably deal with those a bit later. These immediate ones would be useful to deal with though, so perhaps next time I'll look at encoding immediate operands and just see how that goes. But it seems like scaled index and SIB and everything is working just fine now.